Why is it that when certain materials are cooled down to a specific temperature, their electrical resistance doesn't decrease gradually, but instead drops instantaneously to zero, almost as if someone flipped a switch? In energy filament theory, this phenomenon isn't some mysterious magic. Rather, it's an unusual and fascinating reversal of what we typically expect. Instead of the field controlling the particles, it's the particles themselves that group together first, effectively locking the vibrational modes of the field within the material. Let's begin by looking at a typical metal. Picture the electrons as individual travelers, each moving along their own path across a bumpy road. Some of them bump into atomic lattice points, others get caught by impurities, and some trip over each other as they move. When an electric field is applied, it's like a voice calling out from an incline, saying, "Move this way." The electrons move together, but they still encounter obstacles, fall into holes, and take sharp turns. This creates a series of tiny vibrations within the energy sea, which we perceive as electrical resistance and the generation of heat. Now, when the material enters a superconducting state, the entire situation changes dramatically. At extremely low temperatures, the electrons are calmed down enough that they pair up and move in a synchronized pattern. No longer do they move independently. Instead, most of the electrons within the material start to move in harmony, following the same rhythm in a circular path. Essentially, they create a large and organized near-field texture in the energy sea, which can be thought of as the formation of a collective electron choir within the material. This new collective behavior leads to a massive change in the way energy flows through the material. At this point, the field isn't free to move as it normally would. When an electric field attempts to induce vibrations within the material, it finds that the disordered small motions are blocked by this macro-scale texture. The only kind of motion that's permitted is a large-scale movement, where the entire choir shifts together. The energy sea is no longer able to accommodate the small vibrations, and the typical scattering, friction, and heating paths are effectively shut off. What we observe now is the phenomenon of zero resistance, where currents can flow freely within the material, but the energy is not converted into heat because the normal dissipation pathways are no longer available. Superfluidity operates under a similar principle, though the main players here are atoms rather than electrons. In a regular liquid, the atoms move randomly, and when an external force is applied, they pull on each other, dissipating the force. In the superfluid state, however, a large group of atoms locks into a unified flow pattern, causing the entire liquid to move as one cohesive entity within the energy sea. The field can now only apply force to the entire liquid mass at once, so the motion is smooth and there's little resistance, resulting in what we observed as nearly no viscosity. In summary, the difference between ordinary materials and superconductors or superfluids can be boiled down to this: in everyday materials, the field dictates how particles behave, but in superconductors and superfluids, the macroscopic structure of the material decides the rules first, and a large number of particles align into a unified pattern, which in turn dictates how the field interacts with them. This leads to the phenomenon where the field can only use one type of motion. This is the new, detailed understanding of zero resistance and zero viscosity that comes from energy filament theory. Tap follow, share it on New Physics, Clear Universe.